Chapter 16, Basic Chemistry, Pearson. Nuclear chemistry is what we're talking about. Natural radiation, that's a pretty important concept. Nuclear radiation, radiation measurements, half-life, okay, and radioisotopes, medical applications of radiation, nuclear fission, and fusion. We'll go through this entire set, and as always, if we need a math session, we'll pause and we'll go through those. All right? So again, the lecture doesn't always reflect the math part. So, natural radiation. Most natural occurring isotopes or elements up to atomic 19 have stable nuclei. In other words, elements have what's called radioactivity. So it's not a scary word, right? It's just which ones have an impact on us. Okay, so they have these what's called radioactive components. Reactivity comes from unstable nuclei found in elements of atomic numbers 20 or higher, defined as nuclei in which the forces cannot offset the repulsion between the protons. And this is what happens: that are radioactive, emitting small particles of energy called radiation to become more stable. So again, with these lectures, you want to make sure the concepts of what we really want you to pay particular attention to. And the bottom line here is that these elements have radioactive nuclei. Okay, and we call it that because what they're emitting this to try to become stable, and that's their goal. Okay, so they're emitting this radioactivity, seeking to find a stable position. All right, stable energy position. That's why it emits radiation, and it does it and likes to do it as quickly as it can, and it does it in many cases where when it's doing it, it's harmful to biological species, or in some cases, it may become explosive. So that's what's happening. All right. So it really means no harm. It's really trying to look out for itself, trying to become stable. You get it? All right. Radioactive isotopes, unstable nuclei, emits radiation, can be one or more isotopes of the element. And when we talk about isotopes, we know the isotopes are influenced by the number of what? Neutrons as well, right? So you have isotopes. You know the protons are what? Always the same? You can identify any element by its protons, right? And that is the proton, because the proton is equivalent to the atomic number. Now, I should make sure, because we're talking about nuclear chemistry, I should say you can identify any element by its atomic number, okay? So that's really how we can identify any of them. And that atomic number is equivalent to the number of protons, okay? Properly spoken. That's how it should be. Okay, so it includes mass numbers in its name. Iodine 131 is a radioactive isotope of iodine, and this is how it looks. Notice the number. The atomic number is 53 for iodine, and this is 31, and therefore these are protons plus neutrons, which you already know. So here we show you examples. We do not expect you to memorize all of these. We expect you to be familiar with them when you see them, to know that this means it must have a radioisotope. Get it? The atomic number does not change. Okay? Note here for magnesium, we have 12, 12, and 12. But what happens? The mass number changes, 24, 23, and 27. If the mass number changes, therefore what changed? The number of neutrons. And that is what we want to make sure you understand. And therefore you have a heavier and lighter iodine. You'll hear people say that. Okay? Or, well, you don't hear as much now. You hear a lot of. You can always tell a guy who's studied chemistry prior to 1970, he'll say light and heavy. You know, okay, it's just the way it is. Okay, so we have iodine here, 127, 53, 53, 53 for the protons, but notice again the change in the mass number. Okay, and here we show you some others for uranium. So these are examples of stable ones. Now, when this happens, they decay or give off radioactivity of certain types. Okay? And each of these radioactive forms has a very specific name. It's like naming your children, like naming your pets, your dogs. That's what they're called. So yeah, you'll have to learn these names, okay? So here we have alpha particles, okay, identical to helium. So we have a nucleus here. It's called an alpha particle. It's +2, and this is how we know it's alpha particle. It's +2. Beta, you'll have to find your own way of memorizing these, right? And so beta is negative. Notice here, the number here, okay, and the number here. Here, beta doesn't contribute to any mass. And you probably would have guessed that when you saw it was a negative, did you not, right? You would have guessed that because you're familiar with that when it comes to electrons. So similar principles are operating here. But you also have these positrons, which they write as beta plus, okay? But also, again, note, there's no contribution here. The top number contributes to the mass. Because you know that because you saw it back here, right? The isotope here, the top number attributes to the mass, and the bottom number is the number of protons. So here we have both beta plus, which is called a positron, and you've probably heard of the positron. If you've ever watched Star Trek, particularly The Next Generation, they'll talk about the positron network, positronic network. This is what they're talking about here. So you hear a lot of these terms in science fiction movies. If you watch Guardians of the Galaxy, you'll hear some of these terms coming across. And this is what they're really talking about. Pure energy called gamma. And it really kind of shocked everybody. Everybody, wow, that's really cool. Well, they just picked up their freshman chemistry book and they read the term and said, well, that sounds really cool. Let's put it in a movie. Okay? And there we have it. So, and then we have gamma. Gamma here, you note here. But gamma is very harmful to biological systems. So I want you to keep that in mind. Gamma, this is the Incredible Hulk. Okay? So gamma radiation is very bad for animal life, and so that's one take-home message from this that we like to hang on to. So when we do this, we have all these different particles. I don't expect you to memorize these again because of where we are. This part of this lecture and the next lectures are exposure lectures. Okay. And there are concepts that we want to make sure you're exposed to and that you have some understanding of. So we're not requiring you to memorize all these, but you do have to know what it's alpha particle, beta particle, right? It's gamma. You know the proton and neutron, so nothing here to really memorize. So these are the challenging ones to do, okay? Ionization radiation strikes molecules in its path. So if the molecule's in its path, it's going to strike it. It damages cells, okay, most sensitive to radiation. And this is what happens when you cancer treatment radiation. You're trying to you're destroying, you're attacking something, and you're actually destroying it with the plan to restore it and to help it restore it to some healthy state, or to destroy it, and you learn to live with that portion over the cancer, okay? So cancer cells are highly sensitive to radiation. Large dose radiation are used to destroy them. The normal tissue around the cancer cells divides at a slower rate and suffers less damage from the radiation. You get it? So it's like, the most aggressive is the cancer. And so you say, yeah, the radiation is causing some deterioration, but that deterioration is deterioration you can live with. And as biological beings, we sometimes choose to live with certain things. Like, for example, when men reach a certain age, when it comes to testicular prostate cancer, many of them will choose to live it out because the decay of that is less than the radiation. Okay? So it's these choices you make. So this is why, but when you're young, radiation treatment is very, very, very important, okay? All right? Because the rate. It's all about rates, maximizing the rates. Okay? Radiation may cause mutations, basically, et cetera, et cetera. And that's what happened with leukemia And this is what happens in uncontrolled radiation, particularly gamma radiation. This is why they have you put the cape on at the dentist's office and other places when they're doing it. Well, actually, yeah, you put the cape on and she leaves the hygienist leaves the room, he or she. Radiation protection require paper and clothing for alpha particles. Paper and clothing for alpha particles is good enough. So a lab coat and gloves for beta particles. You get it? And a shield is required and concrete wall for gamma. And so be aware of this. Okay? So you have alpha, beta, gamma. And as you go, so you may already know your those Greek alphabets. So you have alpha, beta, gamma, delta, etc. So you have alpha, beta, and gamma. So it starts with less harmful and more harmful when you go from alpha to beta to gamma. So we expect you to know that order of harm to biological system. Alpha is the least harmful and gamma is the most harmful of these that we're talking about. Okay? Increases the distance from the source. This is why some people don't like some of the areas where they test for nuclear power and things of that nature because it could lead to some radiation. So here it shows you the example here, okay, of protecting you, being protected from it. So the bottom line is not all radiation has the same impact against biological systems. Okay. Properties of radiation shielding, just kind of show you here. Again, this is a summary of what we already talked about, and so you can get away from it in terms of distance. But alpha particles tend to be okay, not okay, tend to be less harmful. Better choice of words. Okay, and gamma is again harmful. When we talk about radioactive decay, and you're going to see this a few times in different forms and for different reasons, we start with this nucleus right here. In this case, uranium. And we get particles that fall to alpha particles, and it falls to a new nucleus, thorium. And if it keeps going, it will fall to another one and give off a particle, and another one and give off a particle. And you're going to see that. That's what keeps happening, is seeking a stable position. Okay? Lead is one of the places it tries to get to. So here, when this happens, we start with uranium at this isotope. The top number, and you want to note that, represents the isotope. Okay? All right? So you want to be aware of that. These are the types of concepts that I would ask you about. So the top number represents the isotope. And we have here 92, that's the atomic number, which means the number of protons. And so because it's a chemical equation, it has to be balanced. Everything on the left side has to balance on the right side. The amount of energy, protons, neutrons, electrons, mass, everything, because of the law of conservation of matter. You can't destroy nor create matter. So to do these problems, they're fairly straightforward for you because you know how to write balanced equations. And when you write the balanced equation, you simply add, with regard to radiation and radioactive decay, note here that 234 plus 4 equals 238. Does everyone see that? This is the math you'll have to do right here. You'll simply have to add these numbers. That's it. Okay? Does everyone follow? Okay. And it's like doing the protons, neutrons, electrons. I have to give you so much. Usually you're going to be missing one or two numbers. So for example, here you might see 238 uranium. Right? And here, I will put thorium. Where would you get the 90 from? Periodic table. Very good. Then you have to do math to get here. So if this is 90, then you know this must be what? 2. Does everyone follow?
Yep.
Okay. And as soon as this was 2, this must be 4 because it's helium. This is how it works. Okay? Smoke detectors. Okay? They have americium-241, which undergoes alpha decay. Alpha decay can be protected by what? Simple paper and clothing. Get it? All right? Generally not as harmful to biological systems. Alpha particles collide with air molecules. Charged particles are produced that generate an electric current. Okay? So we can write the balanced equation for that. So it generates an electric current. If smoke particles enter the detector, they interfere with the formation of charged particles in the air, and electric current is interrupted. Beep, 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 beep. The battery sets off then. Okay, or whatever, yeah. It goes, it starts to beep. So that's what's happening here. So this is one way that radioactive decay is used. I might ask you that type of question. Okay? Is radioactive decay used? It would be a true false, of course, right? Radioactive decay is used in smoke detectors. The answer is true. Okay? So I expect you to know that.
So how often, at what rate does the average smoke detector run out?
It's like what rate? I think I understand the question. Always. It's going all the time.
Well, I mean, because they say to replace your smoke detectors every so often, and is that the reason why?
That's the okay. Yeah, that's why they tell you every so often your smoke detector, a 40-year-old smoke detector, ain't a smoke detector anymore. Okay, because of radioactive decay. But you're going to learn. I want you to come back to that question a little bit later too, because you're going to learn what's called the half-life of these. And I don't recall the half-life off the top of my head, but it's in a chart somewhere. It's going to come up in this. I think this one's. I hope this one. If not, we're going to look it up. Okay, but it depends on the half-life of the material. Okay, and some things have a half-life that's way past our lifetime. Okay, and I don't recall what it is for this. But that's a very good thought. But that's why they tell you to do that. Yes, that's their concern. Because even if they know the half-life, for safety reasons, aka insurance reasons, nothing can be guaranteed to that extent. They usually kind of subtract 50% or off of it. Say, well, if it lasts 10, you got to insure it for 5, something like that. Yeah, it's a good question. But that's why, yes. So here we have it. So you can do this now, right? So what's going to be at the top here? Give me the value.
237.
Yep, 237. And what's going to be here? Which is, look, somebody do it for the periodic. There you go. You guys got it. What's it going to be? Periodic table. Find it there. What is it? M.
N as in Nancy.
B.
P as in
P.
Paul.
Paul. Thanks. Okay. NP. I not only don't see well. I don't. Okay. Thank you. But that's how you do it. One thing, at least, I'm really happy that I see you guys know how to use the periodic table. Okay. All right. All right. A lot of information is looking at you. Very good. So there you go. Oh, it's right here on the slides, isn't it? Duh. Okay. Does everyone get it? All right. Beta decay. So that's alpha. And we know where it's used. Beta. A neutron in the nucleus breaks down into a proton and an electron. This is just a rule. This is just what they do. Okay? And this wasn't something scientists thought of to give it. This is what it was doing, and scientists named it. Follow? Once they discovered what it was doing, that it got a name. Okay? And so the number of protons decreases by 1, electron beta particles emitted from the nucleus, an atomic number increases by 1, and the mass number remains the same. I will not ask you to memorize all of that, okay, at this point in the semester. What I do expect you to know is how to Solve these and tell me whether it's an alpha, a beta, or a gamma. Okay? I do expect you to know whether it's alpha, beta, or gamma. And notice again, increases by 1. If you know it, I'm not going to quiz you on that. That's not going to be true, false. If you can do these, then you're okay. So here we have carbon 14. Where did we get the 6 from? Where did we get the 14 from? Had to give it to you, right? Mass number. Right? It has to be given, or you have to know it. You don't look on the periodic table for the mass number. Don't do that to yourself. You got it? You have to either know it or I have to give it to you. All right, so here we have radiation, a beta. So no, we know it's -1, right? E, no contribution to mass, is it? Okay? All right? You know that about the negative particles. It's stable, makes a stable nitrogen. So that's pretty cool. And so when we balance the equation, so I think you guys can do this. Okay? No one panic when you have to do this. Just balance it. Okay? So, writing the equation for it, radiation, isotope, yttrium-90, beta emitter. You've heard that already, right? You guys have been hearing these kinds of terms, beta emitters. You have to have heard that somewhere. If you've been around the medical field, any at all. It's, so this is what it's talking about here. It's used for cancer treatment. Okay? Used for a colloidal injection. You know what a colloid is, right? It's the particles. You studied that in one of the previous chapters. And in large joints to relieve the pain caused by arthritis, right? And that's really kind of a good thing. Okay? And the interesting, arthritis is pretty interesting in itself, right? It kind of becomes arthritic because it's trying to avoid the pain. Your joints are trying to not have the pain, so they build up a barrier to not have the pain. But as coincidence to build up the barrier to not have the pain, you get pain. You get it saying, "Oh, I need a barrier between that," and it grows, it builds, and you say, "Oh, gee, that hurts." Okay, so it's kind of one of those events that's kind of interesting here. Okay, write the balance equation for beta. You can do that now, right? Because you now know here, that's -1, so this has to be, okay? Has to be what? You got a -1. 40, right. You get it? So then you go to periodic table, you see it's 40. You do the math at the top. This is 0, so this has to be, you get it? And that's how we do it. That's how we know for a beta. Okay? Gamma rate. So then we have gamma. So beta is more. So alpha is least harmful to biological species. Beta is a little bit more, but gamma really is not so cool. Okay, beta is very useful for medicinal purposes. Gamma emits from unstable nuclei indicated by the symbols M following the mass number. The mass number and the atomic number of the new nuclei are the same. Notice here. Okay, when it's a gamma. So this is somewhat this is like this is as if the element has been frustrated. Okay, it's the same element. It's just you get it, and this is what gamma does.
So it's angry like the Hulk.
It's like the Hulk. It really is. That's why I like to use that example. It's just frustrated. Okay, and it's coming out as gamma. Everything else is the same. You say, what's the problem? Okay? All right? All right? And so, here, we've summarized them all. Okay? So we have this. You have that down, right? We're good? So here is a summary of them. Alpha, you know what happens, right? Beta, here. We didn't show you the positron, but here's a summary of the positron. And then we have gamma. The ones that I'll be focusing on for this class are the alpha, the beta, and the gamma. Okay. Radioactive isotopes, slide 20. Slide 20 in this lecture. Radioactive isotopes are produced in a process called transmutation. This is what happened in the Ninja Turtles. Okay. When a stable nuclei is more radioactive by bombarding it with the small, high-speed particles such as alpha particles, protons, neutrons, and small nuclei. And again, this is what happened again to the Ninja Turtles. Okay. And Shredder as well. So here you have bombardment of the particles. And it goes here. So this is the particle. This particle gets hit with helium. Get it? It's like it goes in it, pops it. When that happens, it kicks out here. Okay. Does everyone follow it? So kicks out a neutron. And you have a new radioactive nuclei. And this radioactive nuclei has to do something. And what will it do? It will decay. That's the message over and over again. It has to decay because it's seeking to be stable. Okay? So here, and this is what happens in a nuclear power plant, by the way, and you're going to see that today as well. You have the stable nuclei sitting there, minding its own business, and then it gets hit with an alpha particle. Now it's really agitated and needs to decay. And that's what the Geiger counter measures. Sees whether or not this is happening. Okay? Has it been hit? So it has one signal here by itself, has another signal when this happens. So it kind of goes, you get it? That sound you're hearing? And the sound is simply there for us. Okay? You got it? Okay? It's like the stud finder, right? With the battery in it. Kind of goes, the sound's on there for you. Okay? It can do its thing without the sound. Okay? So it gets the Geiger counter and it counts them. So, and these are the units, and this is how they are measured. I simply expect you to be exposed to this. Okay. It would be units of radioactive measurement, R. It would have Curie, Rad, Rem, and then that would be a multiple choice. That would be the correct answer. Anything other than that would be the incorrect answer. So simply expect you to be exposed to these. So this is a slide you want to mark. Slide 22 in this lecture. Know these. We're not requiring you for this course to do this part of the math. But we expect you to know the concept once you see the math. So, here's how we measure it. Okay? A dosimeter, real cool name, right? Dosimeter. And some will say dosimeter, depends on how you pronounce things. Measures radioactive exposure. And so you probably, if you've been around, you've probably seen people who wear similar badges that work in NMR, MRI, CAT scan things. They'll wear these types of devices. They'll wear these types of tags in other areas as well. And so here, average annual radiation by a person in the United States is shown here. Okay, the amount is naturally there. There's a large amount of just natural radiation. Here we show you what's happening with X-ray. Okay, and radon, which radon comes right from indoor exposure. Those who burn candles and incense and things of that nature, you want to air your house out occasionally. It smells really great. It's really wonderful. But yeah, it's just a wise thing occasionally when you do that, open the windows. You'll know if you got it. You have radon poisoning. You'll feel like you've been treated for cancer. Similar symptoms: nausea and overload. Chemical link to radiation. The Center for Disease Control and Prevention estimates in the United States 20,000 people per year are infected. Wow, that's pretty good, right? E. coli. That's a lot. 500 people each year die from E. coli contamination. E. coli has been responsible for outbreaks of illness containing ground beef, fruit, vegetables, etc. And this is why this is the area where you use radiation. That's where we're headed with this. The FDA has approved, 0.3 to 1. Here we are. Cobalt, all right, or cesium. And note here it says cobalt what? Just to say cobalt what? 60 is important. Here, cesium 137, okay, for treatment of foods. So this is approved. So this is an example where you're using the radiation. It's helpful because it's going to go after that small E. coli organism. It's going to zap it essentially. Okay, kill it before it kills you or me. Cobalt pellets. Okay. And arranged in racks. Food moves through it, and there you have it. Okay? Does everyone follow? So the take-home message here is that radiation is used to purify foods. Okay? That's what we want to expose you to. When the bacteria is killed, it does not contain the radiation source, and it does not become radioactive. I smile and I laugh because this is one of the biggest marketing gimmicks going today. Buy our food because it's never seen radiation. And they tell you, did you know they treat that your fruits and vegetables at the whatever store, treat it with radiation? You go, oh, no. Okay. And what do you think happens to all that radiation? Where does it go? It's got to go somewhere. It is a big late night commercials. Okay. Scare tactic, and it works, which makes you pay more. You're paying a little more for your food, but it's not radioactive food. Your food is not radioactive, folks. Okay? All right? Now, if you think it is, it's up to you. But there's no science related to it, and that's what we want to make you aware of. Okay? Exposure to radiation of less than 25 rem usually cannot be detected. 100 rem, whole body produces temporary decrease in white cells. Of over 100 rem may induce radiation sickness. You get nausea, vomiting, etc. Whole body dose, 500, may cause death in 50% of the people exposed.
Have you watched the show Chernobyl on HBO yet?
I haven't seen it on HBO, but I've seen a lot about Chernobyl.
The series that they did is just a little mini series. It's pretty interesting. I enjoyed it. I haven't seen that series, but I've probably seen everything else. Not everything. It's just astonishing, like the touching of the radioactive material, and literally like seconds later, their skin was burning, and it's just.
It is that, and we're gonna actually. I don't know if we have it in this one. In one of the classes I teach other places, I actually go into detail on it. I actually have students do a report on that, because it's just one of those things that's just eye-opening for you. You go like, whoa, yeah.
You know, since watching that, I've delved a little bit deeper into learning more about it, and it's crazy.
It is. It's for science. It's a fascinating area of science that, if not properly handled, it's devastating.
Yep.
Okay, it is very unforgiving. Okay, it attacks and it just keeps on attacking. Okay, why is it doing that? It's trying to become stable. It's looking for a stable nuclei. Okay? And that's what's happening. Yeah. No, I haven't seen that one yet. I'll probably see it now.
Yeah, I recommend it.
Okay, I'll take a look at it. I haven't seen that one. Legal doses of radiation. So, I'm sorry, lethal, not legal, lethal doses of radiation for some. So insects, okay, bacteria, rats, humans, dogs. So you see these, okay, the insects can really hang in there, right? You kind of.
They have the hard exoskeletons?
No, yeah, it's that and the rest of their gene code.
Internal makeup.
Yep, yeah, but it's all those things that contribute to it. Now, you're thinking about that now, right? Like, because you saw earlier the covering, the whole bit, all of that goes into radiation and how it affects us. Yeah. Bacteria, and this is why you zap it pretty good. Zap. You treat it with radiation, okay. And rats, okay, humans, and dogs. So dogs, you see, your dog really can, kind of get your dog right away. So your dog's almost an indicator. Something's not right, okay. All right. Let's take about 5. We'll keep going after that. You good?
I think so. That's
Good.
it's gonna get. Yeah.
Yeah. Yeah.
At least you didn't pull that off. But you shouldn't pull that.
Okay, let's continue on. Lethal doses of radiation for some life forms shown here. Again, insects, bacteria, rats, humans, and dogs. We expect you to at least know and understand, or at least be familiar with, insects can resist it more than dogs. That is the take-home lesson here, okay? It's that these organisms can handle it more for their design, based on their genetic design. So, radiation, in theory, doesn't last forever. It reaches an asymptote, like in math, right? And when it reaches a certain asymptote, we say it's not there, but it's always there. So you get it? So in the sense, we say it doesn't last forever, but some form of it goes asymptotic and never reaches 0. Does everyone follow that? Okay, goes to the asymptote. But for all the practical purposes, we can call it 0 or call it no radiation. And when they report it, they never say no radiation. They say no detectable harmful radiation. You get it? Okay? All right? So here, but it goes in half-lives. And this is why handling radiation and being familiar is so important. The half-life of a radioisotope is the time the radiation level active to decrease half, 1/2 of the original value. And so it goes in these half steps. Does everyone follow that? Okay, and this is a math that I expect you to at least be familiar with, and I'll let you know next week whether we're going, how we'll test you on this, okay? It will very likely be a multiple choice type question, and you'll look for, it goes in half, then that half goes half, then that half goes half. Does everyone understand how the halves go? So if it starts at 100, it goes to 50, right? Once it hits 50, then it goes 25. It's 25, it goes 12 point, you get it? So if you see like 12.25, you just double up, and you say, that many half-lives. You get it? So it's always, that's how it works. Okay? So here we show you an example of this 20 milligrams to 10 milligrams to 5 milligrams to 2.5 milligrams. That's how half-life works, to go to that. Now, each radioisotope has a different half-life. And for some, that half-life is beyond our lifetime. And that's what concerns people with handling radioactive waste. Okay? Here, the decay curve illustrates it. 1 half-life, 2 half-lives, 3 half-lives. 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives, 7, 8, 9, asymptotic, okay? Never reaches a true absolute zero. Here we show you examples. I expect you to memorize in this entire table 16.7. No, I'm just kidding. Okay. All right, this just shows you examples of the half-lives. But here's what I want you to pay attention to. Note here how long it takes to reach its half-lives. Carbon-14, 5,000 years to reach a half-life. This is why you can use carbon-14 for dating, what's called carbon dating. This is why, because you know you can look at what the concentration is, and you can back calculate really smooth, really clean, right? And it's non-harmful to biological matter. You get it? So you can look at the carbon the C14 radioactivity in something they dig out of the ground. Take it in a laboratory, measure it, and it has some concentration. And simply, they take out their dimensional analysis tool. No, then they take out, they put it in the app. Okay, they put it in the computer, spits it back, runs the numbers for it. But you could calculate by hand, right? But you have to do a lot of it. Find out how many millions or billions of years that it's been there. Potassium, 10 to the 9, 16,000. Uranium, this, for the alpha on uranium. Look how many years. A lot of years. But look at this, carbon-11, 20 minutes. This is why you would use some of these for medical radioisotopes. Does everyone see why now? Because what? It's reached a half-life in 20 minutes, another half-life in 20 minutes. So by the end of the day, follow, it's pretty much non-detectable. In some instances, when people are taking certain types of radioactive treatment, they'll tell you don't go around people for, they'll say, for an hour or 2 hours. And they'll particularly say don't be around kids or your dog. And this is kind of why. Now you understand why they tell you your dog. Say, why not go around my dog? I love my dog, my little Poochie Poochie, right? But your little Poochie Poochie is more susceptible to it than you are. You get it? Okay, so this is partly why. So here, you notice here, so in a few days, these are gone, and therefore these are good to use for medical reasons. So in cases where it's longer, item 131, with the gamma here, 8 days, just may keep you in the hospital, say, why am I still in this hospital? I feel better. Yes, you do feel better. But we'd like to give you a few more days to get these half-lives. You get it? And to monitor progress. So there are reasons, there are scientific reasons for sometimes where people say, I feel better. It's not a matter of feeling better. Sometimes the treatments there don't allow you to be back out, okay, in the public. So this is how it's used, and this is how it's done. And these are the ones that are used for medicinal purposes. Okay? So what's the take-home message? Radioactive isotopes that are used for medicinal purposes have shorter half-lives. That's the bottom line. Okay? Get it? So their radioactive decay is faster. You get to isotope much faster. So that's the take-home. Those used for medicinal purposes have shorter half-lives. Because you'll be, well, you're giving me this radioactive stuff. Isn't that like Chernobyl? No, it's not.
Go to Chernobyl right now and see what's up.
Right.
We'll talk about radioactive.
Yeah. This is gone. You'll be fine in a few hours. You'll be fine. So if you gave them this one, you'll be okay. 28 days. Okay, chromium-51, they might say, we'd like for you to refrain from being here, from doing this, from being around this because of what happened. Get it? All right. So radiology dating is a technique used by geologists and historians to determine the age of ancient objects. The age of ancient objects is determined by measuring the amount of carbon-14, which has almost 6,000 year half-life. So if you start at some concentration, 6,000 years later, it'll be half that. Then another 6,000 years later, it'll be half that. Then another, and so this is slow enough to really make it a nice tool. Okay? And it's within, you see, in other words, is within reason for the lifespan of mankind, not for an individual, of course, right? But for the span of mankind, it's reasonable. And so what do? Here it is. We have what? Carbon-14. So we know that a neutron, cosmic rays, hits the nitrogen-14, and this is what's called nitrogen-14. Where we get the 7, we know, periodic table. And carbon, periodic table. Carbon-14, and it has protons. And this is how it decays. Okay? So carbon-14 is produced in the upper atmosphere by bombardment of nitrogen-14 by high-energy neutrons from cosmic rays. C14 reacts with oxygen to form radioactive carbon dioxide, which is absorbed by plants. So you have this C14, and it now reacts with oxygen, and we get radioactive carbon dioxide, which is absorbed by the plants. Okay. So this is part of the cycle. So the plants absorb it, right? And so the plants are radioactive, but it's non-harmful radioactivity. You get it? Okay. Here, dating objects uptake C14 and carbon dioxide stops when the plant dies. So when it dies, okay? As carbon-14 decays, the amount of radioactivity decreases. Of course it does. You get it? And it's decreasing by what? Half-lives. In the process called carbon dating, scientists use the half-life of carbon-14 to calculate the length of time the plant died. Okay? And that's what it's used for. This example here, showing here the Dead Sea Scrolls, obtained using carbon-14. It was written on Piper's wood fiber plant. So, which is carbon. So they were able to use it. Other examples, bones use number of half-lives of bone, tells you the age, because carbon-14 is almost 6,000 years, 5,730 years to be exact. The bone sample has 25% of the activity of C14 found in the living animals. How many years does it have? You just run through the calcs. The age of the bone sample, the skeleton can be determined by carbon-14. Here we show you the calculations. For this class, we're asking you to be familiar with the calculations. I won't be asking you to learn how to do them independent of simply seeing them, plugging in formulas, and punching the numbers. Everything for the carbon dating, if you have that on the exam, will be there. You'll simply have to put in the numbers. So you say, but gee, what am I going to learn from this? You know I'm going to look for those sig figs. Yeah. You get it? Does everyone follow that? Okay? So this is you'll be using it like everyone else, you'll be using the app. Plug and play. Okay? So 100% activity, you go down to 50% for 1 half-life. 2 half-lives goes what? 25%. How many think you could probably do this, right? Just plug and play. 1 half-life, 2 half-life, 3 half-life, 4 half-life. You get it? Okay? So that went half, that's half. What would the next value be, by the way? So you get it. And that would be called 3 half-lives. Okay? Okay? So you see something like this. You see the values, and I'd ask you to put in half-lives, or you would see the half-lives, I expect you to put in the values. Okay? Plug and play. That's it. Here, then we take it, we run through the calcs to get here. This is our good friend, what? Dimensional analysis, right? So we got the half-lives, we plug it through, and here you get it. Okay? All right? For these, again, we have a math session. We'll work through more details. Again, I think you're aware of that. We work through the math details later. Radioactive isotopes with short half-lives are used for nuclear medicine. We've already talked about that. Have the same chemistry in the body as non-radioactive atoms. Have the same chemistry, but it's a way of tracing it. The doctors say, well, put a tracer. Okay? And this is what they'll do. Okay? And they'll follow it through, and that tells them how your biological system is working. They'll extract the fluids, and they'll extract, oftentimes they'll extract from cadavers too, and see where the radioactive materials were. That tells them how it went. And here, this is pretty cool. Gives our radio action that exposes to, okay, photographic plate scan, gives an image of an organ. Yeah, this is what's happening. This is why you take those, when you go for your scans, and they ask you, are you sensitive to certain types of dyes? They use the word term dyes and things of that nature, meaning these are radioactive, and they can trace you in that way. You get the scan, and there you have it. Here, we're not going to ask you to memorize these. Just be aware of them. After the patient receives the radioisotope, the radiologist determines the level and location of reaction emitted by the radioisotope. Gamma rays emit the radioisotope, and the organ can be used to expose a photographic plate, producing a scan of the organ. And this is where we use incredible. Okay. It allows them to take a photograph of it because of the interferences. Okay. Thyroid scan shows accumulation of item 131 in the thyroid. So it's run, and the one thing is it's color coded now. Positron emission. Positron emissions from emitters of C11, oxygen 15, and fluorine 18. You know how to do these calculations now, right? And we would do these separate discussions, but it must be balanced. You have fluorine 18, the 9 atomic number for our table. It decays to oxygen. Notice something here, that this decay is to monoatomic oxygen. Very important. If I say oxygen gas, okay, or reaction with air, that means O2. This is monoatomic here. Okay? Those protons here, the nucleus, so O18, and a positron, which doesn't contribute to mass. Positrons combined with electrons produce a gamma ray that can be detected given a three-dimensional image, so you hit it with a gamma ray. Okay. Positron emissions and emitters are combined with the body. Substances such as glucose. Positrons are used to study the brain function and metabolism. I really like for you to know this statement. It'll be a true-false type question. That's what positrons are used, because I just think that's the most important thing to know about them. This is what you're seeing when you're doing this. Okay. Studying brain, so positrons. I thought it was so cool that positrons for the brain. Okay. Yeah. Okay. So it's easy to write positron, positive brain. Okay. Your computer technology here, when using computers, 30,000 X-rays are directed at the brain in layers, are absorbed at different rates due to the differences in density of body, tissue, and fluids. This is computed tomography. And so it basically is creating an image of it. And tumors for hemorrhaging, so CT scan. Okay. So you're hitting it with pretty powerful X-rays, right? CT scan here. Yellow shows the tumors, and again, this is all color-coded after the discovery. Okay, so the colors are there, and that's what they mean. So the colors, except they are assigned, mean nothing. You could have signed them. If you had invented it, you would have signed it a different way. Okay, these are the colors as they're assigned. Okay. MRI. MRI years ago used to be called nuclear magnetic radiation. But that word nuclear scared people, so they just called it magnetic. Okay? And really, they hardly ever even use the terms. They call it MRI because to the average person out there, the average consumer, they hate hearing the word magnetic as well. So they just call it MRI, and you don't really know it stands for magnetic. Okay? So here, MRI is based on absorption of energy with protons and hydrogen atoms and excited by a strong magnetic field. So when this happens, it creates an image basically through some form of an interference. The protons align with the field and resonate with the different frequencies, which is then picked up by the scanner. So it basically zaps it, and there's some algorithm that's written, and you get the image, and we call it MRI. So we talked about the general concept of nuclear chemistry. It's radioactive decay. It's radioactive decay because the nucleus are trying to reach a stable position. That generally we'll see alpha, beta, and gamma particles. We know that we have positrons and we have neutrons as well. We know we have beta emitters, etc. And the form of these are used for medicinal purposes, and they're used for historians to do carbon dating. Again, this is because we have the radioactive decay. Radioactivity is also used in foods, and your foods are not radioactive after you treat them. Okay. We also note that dogs are more susceptible to radiation than humans, who are more susceptible than insects. Radioactive decay is also used simply because of its energy content. That's what we're going to take a look at, nuclear fission. The energy content, okay, is so large compared to fossil fuels that it's worth investigating as a source of energy, and is used and understood as a source of energy. And that source of energy comes through what we call nuclear fission. So in nuclear fission, a large nucleus is bombarded with a small particle, and you can guess what that might be, right? That small particle, right? The cosmos doesn't naturally there, but this could be what those helium particles could strike it. The nucleus splits into smaller nuclei and several neutrons. These neutrons reattack. Large amounts of energy are released. So you get this large amount of energy that's released. The energy generated by splitting the atom is called atomic energy. So this is essentially, fission is essentially atom splitting. Okay. When a neutron bombards uranium, an unstable U-226 is formed and undergoes fission. Small nuclei are produced. Proton 91, barium 142, the neutrons released to bombard more. Uranium-235, and it goes on and on and on and on. And it keeps going, looking for a stable place, and that's what this slide shows. Slide 50 in this presentation shows it here. A neutron bombards uranium-235, produces uranium-236, which is unstable, and it splits, right? Into krypton 91, barium 142. Here, these nuclei these neutrons fly out of here, 3 of them, and it has to be 3 because it has to be balanced, right? Does everyone understand why it's 3? It has to be balanced, okay? And you balance these coefficients in front of these, by the way, just like you balance your other equations. You do not change the superscript above if it's given. You simply balance it in front. Get it? Okay? So you have 3 of these, and that's what comes out. And you get this plus energy, and that's a lot of energy. If we could determine the mass of the protons, krypton, barium, and 3 neutrons, we could find that their total mass is slightly less than the mass of the starry material. That's pretty interesting, right? The missing mass has been converted into an enormous amount of energy consistent with the famous Einstein equation, E equals mc squared. And this is a bit of an issue because we tell you it can't be energy cannot be created or destroyed, which means on the left side you should have the same numbers, and over here you should have the same numbers. But you don't quite have the same numbers here because in that transformation into energy, there's a little bit of loss somewhere that's yet to be harnessed and fully understood. Okay, this is Berkeley type research. Okay? But because of Einstein's equation, we can work with the values. Okay? So we get this, and it's called a chain reaction. So that it starts to fall apart, and it keeps falling apart, looking for those stable isotopes, right? And fall apart at what rate? Half-lives. And each has its own half-life. So the half-life, so you're going to get a half-life here, you're going to get a half-life here, you're going to get a half-life here, half-life here. These half-lives are different. It's going to create a new one. It's going to get a half-life, it's going to keep, you get it? So you're going to get radioactive decay on and on and on through an isotope, and that's what's called a chain reaction. To sustain a nuclear chain reaction, sufficient energy of U-235 must provide a critical mass in which almost all the neutrons immediately collide to form U-235 nuclei. In other words, it's called a critical mass. This is why governments around the world are concerned when people are collecting nuclear waste, because you get the critical mass and you get a chain reaction. You get it? So this is why they're concerned with knowing where the radioactive materials of certain types are located, because you get critical mass, you're going to get a chain reaction. Yeah, and it's going to look like this. This is what it's showing. And this is going to keep going, and this turns into Hiroshima. Okay? The dropping of the so-called atom bomb. Okay? And so when this happens, we get this. And it simply explodes and and causes trouble. Okay?
So when they say like dropping the nuclear bomb, like you said in Hiroshima, that's actually nuclear fission.
That's correct. That's exactly what's happening. And now you get it, what's happening to it, because this one explodes, the next, and just keep going. It's not like TNT, you drop it, boom, it all blew up. No, this stuff just keeps going, and it's going at such an enormous rate that it releasing all of this energy, right? And yeah, all the energy destroys what's around it, and then leaves the radioactive decay to keep going for its half-lives. So not only does that physical damage, right, it's going to leave some type of biological damage from it. Okay? And this is a concern with governments around the world in terms of this happening, of something like this happening in a major metropolitan area anywhere around the world. It destroys not only the infrastructure and everything, it leaves that area where you say, you can't live there. That's correct. So nuclear fission occurs at extremely high temperature. So really hot, right? Combine small nuclei and large nuclei, releases large amounts of energy, occurs continuously in the sun and stars. This is why the sun and stars. And we know, right, stars are really other suns, right? Yeah, it's like this, every star there is a sun. It's just what we call the sun is close enough for us to have some form of interaction every day. If you're down south, you're at 100 degrees having that interaction. Here, Here we reach 75, man. We're like, whoa, this is killing us, right? And down south, they're like, they're putting on coats. Okay, scientists expect less radiation waste with shorter half-lives from fusion reactors. Expect less reactive waste with shorter half-lives. And so this is why I understand that half-lives is so important. Okay? So, how might this be used? Well, let's just keep talking about fusion first. I think we should be able to show you, I think in these slides, I think I have that in this slide. Here, it's basically produced here and it's used for harnessing the energy, so to speak, harnessing nuclear power, right? So here, we get these pipes carrying the heat through it, concrete shield. Why the concrete shield? You now know, right? Why you have these concrete shields there is to keep, protect, shield from the radiation. Which one are we really shielding? We worry about the gamma, right? And so we have here, we have these neutrons produced, and from steam generator goes through, and voila, we can harness that, and that gives us a nuclear power plant. And this is what's happening there. This is housed in the reactor, and it's concrete. All nuclear waste, by the way, is required to stay on site. No nuclear waste leaves the site it's on. That's it. That's the law. All the other plans to put it in caverns and stuff in the far Midwest, the Montanas, Arizonas, Nevadas of the world, nope, felt not happening, and probably won't happen. Because the concern is, can you really safely put it underground there and really assure us that it's not going to come out and hurt the indigenous wildlife and people who live there? They say, well, there's a high probability it won't. Okay, gotcha. Which means you will keep it there, and that's what happens. So when nuclear plants are built, they have to have land to also account for that. Okay, so all the plants, you say, why do they have all that land? What are they going to do with it all? Yeah, it's called bury the nuclear waste, and that's what's happening. So here you have fission is used to produce energy. The quantity of U-235 is held below its critical mass. It's held below its critical mass. That way you don't get spontaneous explosions. You don't get spontaneous radioactive fission. Okay. The heat produced in fission is used to make steam and drive generators. So it's basically heating the steam better than heating it with fossil fuels. That's what radioactive power plants do. Okay, nuclear power plant supplies about 20% of electricity in the United States, about 20%. So 80% is fossil fuel. And by the way, power plants run less than 50% efficient. Did I say it in this class? I don't recall. I tend to talk about that. I think it's about 35% efficient. That's terrible, isn't it? They run about 30. Power plants run about 30. Lose about over 50% of the energy just waste. And that's as good as the technology is. Incredible, isn't it? Now you wonder why and that's why when you put a strain on it, it's getting even worse, and they ask you to back off because it's running as hard as it can run. That is the state of the technology. Yeah, I hate to bust your bubbles about that, but that is the state of technology. I think it's now running about 35% worldwide. Okay, and so a fossil fuel plant is running at 35%, is producing about 80% of our energy. You get it? But nuclear power plants aren't running much better than that either. Just the state of the technology, the engineering aspect of it. Mechanical engineering hasn't caught up with that aspect of it. At least that's who the rest of us chemists like to blame, the mechanical engineers. You got to blame somebody. But
when
no.
I worked for Consumers Energy, they told us all that information.
Yeah.
Because I worked there for a long time. But that's why they're going to water power and wind power, and because the fossil fuels, there's just so much waste. That's what we have to do for now, but it's not going to be worth it in the long run.
Yeah. And the problem we have with wind is, can you get enough places to locate wind? Solar, can you put enough panels to operate it? So it's really a catch-22 because as consumers, we want things and we want them now. No one wants to wait for the new cell phone. You get it? And all that requires energy and power to get it. So it's just the way we've created our dynamic for life.
But it becomes an issue with consumers saying, no, I don't want that in our area, like the Muskegon Dam, they closed that for the longest time and just got it reopened. You know, because of
Yeah.
laws and people say no.
Yeah. That's how it is. Yeah. That's how it is. This is actually why, by the way, and we'll finish this. Just one more. This is what happened during the Gulf War when they started to burn the oil. It said, "You want to play this game? You need fossil fuel. So we'll just burn them." Okay. So that was a tactic. Not much different than we used in this country when they burned crops, right? Sports, earth, history. It's all part of this whole thing. You need the energy, and it's not that highly efficient, but it's the best we got. So by the way, that's not a statement against what we are. It's just who we are, where we are. Does everyone follow? Okay. Brings us to this. In a nuclear power plant, the boiler, the heat source that runs the boiler is different. That's the only difference in a nuclear power plant, so please note that. That is a pet peeve of mine, and you will see it on the exam. The only difference is the heat source that runs the boiler is nuclear, not fossil fuel. You do not get radioactive electricity coming at you or radioactive water coming at you. Okay? It's just a more efficient way of heating it. Okay? I think the number is something like 6 to 10 times. I don't have it on this slide. And so it gets it, it turns the turbines. And that's it, folks. You survived the lecture on nuclear chemistry. That's all you're going to get on nuclear chemistry, folks.
Can you repeat the heat source thing?
The heat source, yeah. The heat source for running the boiler is nuclear versus fossil fuel. It doesn't create new radioactive species coming to your home. Okay? So be aware of that. All right, folks. You've been now exposed to nuclear power. That's it.